14.5 Part 2. My only goal in Part 2 is to do a couple of integrals. One in a triple integral in cylindrical coordinates, and then the other one is going to be a triple integral in spherical coordinates. So let's start here. In cylindrical coordinates, don't forget that you need this extra factor of r to do a triple integral. We are given this problem. Notice that the problem is presented in terms of Cartesian. What is the solid D over which the function is evaluated? Looking at the bounds, I see this. Z is between two planes, and x and y together map out half a circle. What quadrants in the xy plane is the half circle? Well, y can be either positive or negative, while x is strictly positive. So that tells me I'm in the fourth and the first quadrant in the xy plane, and that's significant. Let's write our region D in terms of cylindrical coordinates. So first, let's remind ourselves of how cylindrical coordinates work. Very similar to polar coordinates, except for Z, you just have, it just gives you your elevation. And this is what I get from my transfer over to cylindrical coordinates. You might be surprised at first by theta going between negative pi over 2 to pi over 2, but if you think about it, this makes a lot of sense. We need to be in the fourth and the first quadrant, and we want a consistent interval for theta. Next, we need to think about our integrand, and we need to write that in terms of cylindrical coordinates as well. So I use the bounds given me, plus, instead of x squared plus x squared plus y squared, I instead put in r squared. Our first integral is with respect to z, so we're going in between these two planes. I like to move my little factor of r out into the front. R has a way of getting lost or tucked in where it doesn't belong. So I move the r and then I integrate first with respect to z. Next, we want to integrate with respect to r. Now, theta is being held constant. So what I'm doing here in this next frame is I'm just focusing on the antiderivative of r radical 1 plus r squared. If I just focus on that, and then think about what my antiderivative would be and evaluate from 0 to 2 radical 2. And I get 26. Next, integrate with respect to theta. And my function evaluated over the region D is 26 pi. The next example I'd like to do is one in spherical coordinates. Notice with spherical coordinates you have two extra factors, a rho squared and a sine phi. Evaluate this triple integral where D is the region in the first octant between spheres of radius 1 and 2, centered at the origin. That was awfully nice of them to center these spheres at the origin. So with our two spheres centered at the origin, very nicely done, what's going to be our movement of rho? Rho goes between what and what? Well, no surprise, rho goes between 1 and 2. Next, what about phi and theta? Well, I have to stay in the first octant, and so phi is going to start up at 0, that's my positive z axis, and keep moving down until it gets to pi over 2, which is my xy plane. Again, for the same reason, theta has to be between 0 and pi over 2 because I have to stay in the first octant. Next, we need to write our integrand in terms of the spherical coordinates. Well, x squared plus y squared plus z squared is equal to rho squared. And then with a little bit of algebra, I have an integrand of rho to the negative 3. For my next step, I need to remember that I have to add in this extra factor of rho squared and sine phi. So f is equal to rho to the negative 3. And put in these extra factors, put in your bounds, and you'll be all done. And here's what I get. Let's integrate first with respect to rho. That's the first one in order. And my answer is boxed in yellow. Below my answer is my thinking in how I got that answer. And then integrating with respect to phi. Again, below the yellow box is my thinking and how I got that answer. Let's now integrate with respect to theta. And our function evaluated over d, our solid d, is pi ln of 2 all over 2.